The James Webb Space Telescope, or JWST, is a next-generation space telescope designed to be the successor of the iconic Hubble Space Telescope. It's an ambitious scientific instrument that is revolutionizing our understanding of the universe, from observing the first galaxies formed after the Big Bang to studying the atmospheres of exoplanets and hunting for signs of life beyond Earth. Who made the JWST? The JWST was a collaborative project between three space agencies: NASA, the National Aeronautics and Space Administration, which led the project; ESA, the European Space Agency, which contributed scientific instruments and the Ariane 5 rocket used for launch; and CSA, the Canadian Space Agency, which contributed a key instrument, the Fine Guidance Sensor, Near-Infrared Imager, and Slitless Spectrograph, or FGS NIRIS. The development of JWST spanned decades, beginning in the 1990s, and it was a major engineering and scientific effort involving thousands of scientists, engineers, and technicians. When was the JWST made? The JWST was designed over a period of around 2 decades. Officially started in 1996, it went through rigorous phases of conceptualization, design, construction, and testing. The telescope was completed in 2021 after extensive testing and assembly, with the construction process taking longer and costing more than initially anticipated. The final cost for JWST came to around $10 billion. When was it sent to space? The James Webb Space Telescope was launched on December 25, 2021, aboard an Ariane 5 rocket from the Guyana Space Center in French Guiana. This marked a monumental moment for astronomy, as it was the culmination of decades of work. After launch, the telescope underwent an intricate deployment process, as it had to fold up to fit inside the rocket and unfold itself in space once in orbit. The deployment took about a month and was filled with tense moments for the team, as every step had to go perfectly for the telescope to be fully operational. JWST reached its final orbit at a location known as Lagrange Point 2, about 1.5 million kilometers, or about 1 million miles from Earth. This is a stable point in space where the gravitational forces of Earth and the Sun, along with the centrifugal force of the telescope's orbit, balance out. Lagrange Point 2 provides an excellent vantage point for observing the cosmos with minimal interference from the Earth or Moon. How does the JWST work? JWST works by observing infrared light, which allows it to see through cosmic dust and gas that would obscure visible light. Here's a breakdown of its main components. First component is mirror. The JWST mirror has a 6.5 meter, or 21.3 feet, primary mirror, which is over 2.5 times larger than Hubble's 2.4 meter, or 7.9 feet mirror. However, this mirror is made of 18 hexagonal segments that were folded up for launch and had to be individually deployed and aligned once in space. The large mirror allows JWST to gather much more light, enabling it to see distant objects with greater clarity and sensitivity. Second component is instruments. The telescope has 4 main scientific instruments that enable it to observe a wide variety of phenomena. 1. Near-infrared camera, or NIRCam. This is the primary imaging instrument that detects infrared light in the near-infrared part of the spectrum. 2. Near-infrared spectrograph, or NARSPEC. It studies light from distant objects to analyze their chemical composition. 1. Mid-infrared instrument, or MIRI. This observes even longer wavelengths of infrared light, crucial for studying the earliest galaxies and objects that are too faint for other telescopes. 4. Fine Guidance Sensor, Near-Infrared Imager, and Slitless Spectrograph, or FGS NIRIS. This helps in precisely guiding the telescope and assists with studying exoplanets. Third component is sunshield. It is JWST's most remarkable feature. Sunshield is the size of a tennis court, which blocks out heat and light from the sun. This keeps the telescope cool enough to detect faint infrared signals. The sunshield is made of 5 layers of a material called Kapton, designed to withstand extreme temperature variations. Fourth one is cooling mechanism. Since JWST observes in the infrared spectrum, it must be extremely cold to detect the faint heat signatures of distant objects without interference from its own heat. The telescope's MIRI needs to be cooled to below -266 degrees Celsius, or -447 degrees Fahrenheit, requiring a special cryocooler for the job. Deployment in space. After launch, the JWST had to unfold like a complex piece of origami. The telescope's sunshield, mirrors, and instruments were all packed into the rocket, and deployed in space over a period of weeks. The process was complex, but successful deployment ensured the telescope was able to work at its full potential. Range and capabilities of the JWST. The JWST is designed for deep space exploration. Here's what makes it extraordinary. 1. Infrared observations. JWST operates primarily in the infrared part of the electromagnetic spectrum. This allows it to observe objects that are too distant, faint, or obscured by dust to be seen in visible light. It can detect the heat emitted by galaxies and stars that formed shortly after the Big Bang, thus allowing astronomers to look back in time, nearly to the beginning of the universe. 1. Distance and time range. With its advanced infrared capabilities, JWST can observe objects that are up to 13.5 billion years old, essentially peering back in time to just 100 to 200 million years after the Big Bang. This is much farther than Hubble, which observes mostly invisible and ultraviolet light. This deep observational range allows scientists to study the formation of the first stars and galaxies. 1. Exoplanet exploration. JWST is also poised to revolutionize the study of exoplanets. It can study the atmospheres of planets orbiting other stars, looking for signs of habitability or even life. For instance, it can detect the chemical makeup of an exoplanet's atmosphere by analyzing the light that passes through it when the planet transits in front of its host star. 1. Astrophysics. It will study a variety of other phenomena, including the formation of stars and planetary systems, the evolution of galaxies, and the interactions between supermassive black holes and their environments. 1. Detection of organic molecules. One of the telescope's goals is to detect organic molecules and potential signs of life on distant planets by studying their atmospheric compositions for key gases such as water vapor, methane, and carbon dioxide. In summary, the James Webb Space Telescope is a scientific marvel, the most advanced space telescope ever built, capable of observing the universe in ways never before possible. From peering into the infancy of the cosmos to unraveling the mysteries of distant worlds, JWST is unlocking new frontiers in our understanding of space, time, and the possibility of life beyond Earth. Its deployment, after years of anticipation, marks the dawn of a new era in astronomy that will inspire generations of scientists, explorers, and dreamers.